Pretty good deal. Unless they get it wrong, it's because of my sister. My friend Aaron.
Okay, the homework for Wednesday, there's a sheet of problems here at the second link here. And part of that homework is reading in the textbook. And so there's this other sheet, it's called Text and Terminology, which you should have at the side as you're reading the textbook to bridge the gap between what we call things and what they're calling things, okay? So I'll show you that right here. So, they say or write, we mean, okay? They say or write, we mean. So as you're reading, you've got this translator to make the connections between things that may be unfamiliar in terms of what they're reading and then how we've been approaching it, okay? So that you have that, you print that sheet out and have that at hand while you're reading the text. So let me show you the text. So if you go to, this is my math lab, some of you may have bought the physical text, okay? You got it made in the shade. You're ready to go. You've got it in your hand, okay? The section you're reading is 3.2. For those who didn't, you've got it all online. You're going to go here to interactive ebook over on the left, over in these links over here. Okay, and then down here, chapter 3, 3.2. Okay, that's what you're going to read, 3.2. So if something goes wrong, if it's saying can't access the text, or then what you need to do is go back to this home page and do this thing right here, browser check. The browser check is going to help you get the different plugins and little applications that you need with your browser in order to access the text, the interactive text online. So when you click on browser check, it's going to help you. It's checking your browser for all these little things that you need. So this is saying Adobe Reader, it wants to check my version. Wolfram CDF Player, check my version. On these three, I'm all good. Okay, I've got the check mark. So this will lead you through updating your computer and your browser so it can handle the book. That's called the browser check, and that's here at the My Math Lab home. It's the first link right there, browser check. So if you're having difficulty actually getting to the text, it's probably something you need to update with your computer, and this will help you do it. Questions about that? Okay. Questions about anything, homework? All right, so I want to spend...
The problems are in the...
Here, homework from Wednesday, March 6th. So just this is what you're following. Part of it is reading the text. There's a problem on that sheet, and then there's also some problems from the text. So just that handout right there, that post, that file, tells you everything you need to do for the homework. Just go through one problem at a time. Good? Any other questions? Okay, so I want to take some time to review. There were a lot of ideas on Friday, okay? Lots of things going on. And so let's take time to step back, review a little bit. I think it's important that we're not, as we have all these ideas flying around and we're pressing forward, that we're not lost as we do that. So let's do that. Okay, so what did we do first in this class? Did we do rate to accumulation, or did we do accumulation to rate? We did rate to accumulation. Okay, so now we started talking about accumulation functions. Now, so looking back at what we did before, how could we write fx? we spent a month building up a way of writing this accumulation function fx. Okay? So if this is an accumulation function, how could it be expressed in a different way, the way that we took a long time to build up and figure out? Tell the person next to you. See if you're, so everyone should be able to answer this question. How can we express an accumulation function in a different way than just 3x squared, right? So how could we express that accumulation function in a different way? Go.
Yeah.
This is the accumulation of the essential.
Right. Something that we did have.
That's representation. So we need to write it as the integral of
Okay, so let's see how we did. How did we built up all this mathematics and we came up with a representation of accumulation function. That's what I'm getting at. We built up all this mathematics, we came up with a representation of an accumulation function, and what was that representation? Let's see, how about Lauren? Representation for accumulation function. Okay, is that accumulation?
No.
That sounds like average rate of change. Okay, that sounds like you'd be taking this and finding the average rate of change function. So, this, Lauren. Integral. So tell me, what integral? Integral of 3x squared? What do you think? We want the integral of 3x squared?
integral from 0 to x 3t squared dt.
Okay, so our starting point,
A
A,
to x
okay,
3t squared dt.
3t. Well, that,
3t squared dt is what's being offered up. What do we think?
But that's your accumulation
Yeah, so
function.
now we're accumulating accumulation.
Okay, so is it right? Okay, you want to change your mind? Daniel?
I think instead of 3t squared, it should be 6t because you have to put the rate.
So what he's getting at this point here? What goes here?
The rate.
Rate function, right? This is what we did. We came up with a representation of the accumulation. Okay, so if 3x squared is the accumulation function, then it can be written this way. In the integral representation from a to x, integral from a to x of r dt for some dt. And then as we started our journey backward, we said, well, so now we just don't know what r is. So now this is using our accumulation representation. But now it's the other way, because now we have the accumulation, we don't know what r is. So since exam 2, this was kind of the start of our journey here. Well, how do we get the rate given the accumulation function? Okay, so here's accumulation. What do we do first? So review. So let's review this process.
Oh, that's the
This is
accumulation function?
accumulation, right?
Pick a delta x.
Pick a delta x, and then
Draw some lines.
draw some lines. Okay, that's true. Can we be a little more specific? What kind of lines are they?
Average rate of change.
Oh, I was gonna go. I finally had
Judith,
one.
go. Judith.
It's like the slope of each line is the approximate rate of change between each delta.
The
x.
slope of each line is the approximate rate of change for each delta x. Yeah, well said.
Woo.
And average rate of change is essentially what? Average rate of change is? It's constant rates, right? An average rate of change over an interval is a constant rate. Okay, so we wanted to build up a rate function based on approximating constant rates, and those are average rates of change, right? Okay, so our question is, how do we get that constant rate of change? So given it's any value of x, how do we get that constant rate of change? What does it depend on? What do we need? What's that?
Delta y over delta x.
Change in y over change in x. Well, where do those come from? How are we going to get changes in y over changes in x? Somebody knew. Where? So, what change in y and what change in x? Yeah.
Change in y from the beginning of the x interval to the end of the interval, so the left side and right side.
Beginning of the interval to the. So we need the change in y from there to there. So maybe if I could I draw this right here, like this. So we need this change in y, right? Change in x is just what we decided from the beginning. So we already have that, right? We decided that from the beginning. How do we get that change in y? Christina?
You're going to look at your left-hand side of the graph.
Okay.
And,
So let's do our quiz problem at the end. Let's use right instead. Let's use right instead. So how do we use right to define one or both one of these points?
you're going to subtract your previous right from that right.
So let's start with, well, should we start here or here? We're using right. This one? No, you want to start with this one if we're using right of x? Beth,
Start from the other one.
tell me what the coordinates of this point is.
Point A.
No, so this could be any interval, right? Any interval. So we want to use right.
B, F of R.
This is f here? The x coordinate is f? Sharon.
R.
Right of x. And? Yeah, so this is f. This function's f. Or actually in your quiz, it's g. So let's use g. Okay? So it was a g in your quiz. So this y coordinate is? G of right of x. So now, Kaiser, what will the coordinates of this point be? What will the x coordinate be if this x coordinate is right of x? So here we are, this is right of x. So how can we use that to get this x coordinate? Eric, do you know what that x coordinate is right there?
Right x minus delta x.
He wants right x minus delta x. Yeah, we're going to just go back one, right? So what's the corresponding y coordinate for that one? Megan? So we need the y coordinate of that point. That's it. G of, I'm just going to say G of this. Okay, so what's our change in y? G of right of x.
Minus g of right of x.
G of right of x minus delta x. Okay? And then we want to divide that by? Change in x. So this is the average rate of change at any point x, right? The average rate of change on our approximating function at any value x that you pick. Were you close? Anybody close? Anybody get it?
Yep.
That was that. So that was the response on that last question on your quiz. Okay. But how did we do it? We did it based on left x, right? So we started with this point here, left x, left x, and then we got the right side of the interval by adding delta x to left x. Same thing, change in y over change in x. So that's an approximating rate function. Okay, remember this? But what was our goal? Our goal was to get the exact rate function. So the key to that is let our delta x get very small. And let these intervals get very small, and then these average rates will do a better and better job of mimicking the actual accumulation function. Or that piecewise linear function, whose slopes are the average rates, will do a better job matching that accumulation function. And then we said often we use h to represent delta x. Okay, so h is a common use of shorthand notation for delta x. So for a very small h, remember what this, on Friday we talked about this symbol right here. What does that symbol right there mean? Essentially equal to, right? And this is the idea of limit. As h gets small enough, these two values are essentially equal. They're essentially equal. Okay? So another way to write that is the limit as h. Now I touched this pen to the thing. Okay, so the limit as h goes to 0 of, and we also said that as h gets very small, the value of a is inconsequential, and so rather than left, with such small intervals, the difference between just x and left x becomes nothing. It's really the same thing for very, very small intervals. Okay, so this was our, what is this? Is this accumulation from rate or rate from accumulation? Right here. Right, because f is accumulation, and we're building the rate function from the accumulation function. Okay, so that was the process that we went through to build up rate from accumulation. Is this right here, this expression right here? Is this approximating rate function or exact rate function? Exact, because we're saying let h get small enough, very, very small, so that these are essentially equal. And so this is our exact function. Okay. What's that?
So that's where the homework came in, was
Using
the
that.
limit of the actual rate.
So let's do that. So let's do that first one on your homework. Let me just write the, we'll write out our average rate of change. Okay, what have I done so far? So what does that expression mean so far? So let's see. Someone who's in their laptop in the back. Let's see. How about oh, I don't know. Adelaide, what does that expression mean? What's between the interval? So, like the change in x? Change. That's the change in y, right? Because this is the y coordinate where?
On the right side.
Y coordinate on the right side, and this is the y coordinate at the beginning. And so that's the change in y. So to get the average rate, we do
Over delta change in actual h.
h. Okay, so that's our average rate function for an accumulation function f. So we had, we were doing 3x squared, right? So if f of x equals 3x squared, so we are building up this expression right here. So I'm going to rewrite that. So, if f of x is 3x squared, how can we rewrite this average rate expression? It's going to start with f of x plus h. What is f of x plus h? Jatiya. Just this part, f of x plus h. What's that? Starting coordinate. But so if we know that f of x is 3x squared, how could we rewrite f of x plus h? 3x plus h squared. Agree with that? So, like that? Okay. Because what does this function tell us to do? This function tells us to?
Replace x with x plus e.
No, this function. What does the function tell us to do with input?
Square.
Square it, multiply by 3. What's the input of this? X plus h. So we're going to square it and multiply by 3. Okay? Then we have minus
3x squared.
all over. So if we want to find the exact rate function, why can't we just let h get small here? What's the problem? So, like, yeah, Connor.
Because if h approaches 0, then you can't apply the function.
Okay, so basically it's basically trying to start off our process with a delta x of 0. It's like, so we never can get an average rate of change in the first place. So if you go right to letting h be or get very small to become 0, then we miss all those average rates that allow us to actually come up with something to start with. So the problem is, so if we can do some algebra to get an equivalent expression that doesn't have an h down here, then we got something we can work with for a rate function. Okay, so we let if you watched my video, you saw this nice feature. So the first thing I can do is go to math, expand. Oh, that was too much expansion. Let's see. Let me undo that. I just want to expand this. It expanded and simplified at the same time. I just want to expand that first expression.
Can't you pull a 3 out?
Okay, so you want to pull 3 out? But so it won't pull it out of this, so I'm just going to leave it as it is. So we expanded that first part, and now we can, what's going to simplify here? You got a plus 3x squared and a minus 3x squared. So if I simplify, that's going to go away. And so here the point of that is, now we can pull out an h. No, gotta have in parentheses. So now I can pull out an h. And then h over h. So I can simplify that. So what do we have? We have a new expression. What does that expression give us? So what does it mean? What does that expression mean? Anyone want to explain what does 6x plus 3h calculate? Yeah. Exact rate of change. Agree with that?
Almost.
If you qualify something.
If delta x is extremely small.
Yeah, so if h is extremely small. But what if h is not extremely small? Then what? Then what does it calculate, that thing? Okay? It's approximate rate of change, or it's really average rate of change, right? That's our approximate rate of change. So it's the same as this. It gives us the same thing as this for every value of h except h equals 0, right? So for every value of h except h equals 0, these are equal. So therefore, this is also the average rate of change function, which gives us the approximate rate of change. And so then what do we want to do? So what is Rx going to equal? 6x as? So h goes to 0.
Why just 6x? Is the
You tell me.
is it because h is as close to 0 as you possibly can get it?
Yeah, so what if h goes to 0, what does 3h do?
Okay,
Yeah, it's going to go 0 too. Yeah, that's right. Okay, so that was what you did in your homework. Any questions on that?
So then to write that out as a limit,
Which one? This one?
the actual exact rate function is. Would you do that or no?
No, so once we have this, this is the limit, right? So you could write it this way. You could write the limit as h approaches 0 of 6x plus 3h. But that's equal to 6x. And then you wouldn't write the limit anymore. So it's kind of like you're applying the limit to this. When you apply the limit, then you just end up with 6x. You don't have the limit anymore.
Okay, so that's what they essentially equal.
Right. Right. Okay. Other questions? Okay, so we just showed how the rate function is 6x. So we have, if we know that the rate function is 6x, we have another way to express the accumulation function 3x squared. Tell the person next to you, how can you express the accumulation function 3x squared the way that we represented it before? Connor.
Slider and make it go. I guess you get like a 5.
Okay.
The graph itself starts to like offset.
Okay.
Why does that happen?
You'd have to show me. You'd have to show me exactly what you're talking about. Like, if you have some example on your computer, I can't really tell what you mean. So, what will it be? How could we now represent the accumulation function 3x squared in a different way? Sure. She said the integral from a to x, 6t dt, right? Okay, and now that's true for some value of a. Okay, there's some value of a for which this is true. Okay, if we have different values of a, if we consider different values of a, so often then these accumulation functions you'll see in the textbook will be denoted as a capital F. So that's just a common notation. So really, for different values of a, it's going to change it based on a kind of a starting value of your quantity, right? So given a different, depending on where you start accumulating, is going to change the starting value of your quantity, and then you're going to accumulate from there. Okay. So to actually have the accumulation function 3x squared, it's actually 0. Okay, so suppose So let's really talk about the meaning of this rate function. So that's what we're working on now, is getting rate functions from. What does this function tell us about how f is accumulating? How is f accumulating? What does this say? How is f accumulating?
When it's 6 times
What is? So what is that 6x telling us about how f of x is accumulating?
for every x value, you're going to your rate is going to be 6 times that x value.
You said for every x value, your rate is going to be 6 times that x value.
So you get 6x of 1 and 6x of 2 for every x value times 6.
Okay? Other thoughts? Does it mean that, what does this tell us about the nature in which f is accumulating? Connor?
Changes in y will be 6 times the magnitude of changes in x.
6 times the change in x? Always? That sounds like constant rate of change. Talia?
I don't know, I was thinking that the rate is linear, so it's gonna change. I have no idea.
Well, this is, first of all, it's talking about the rate at which f of x is accumulating, right? So let's be specific. The rate at which fx is accumulating is, what does that tell us about the rate at which it's accumulating? So, I wasn't saying that all of the responses so far were incorrect. I was just getting more feedback, okay? So, there may have been some that were close, and there were. The rate at which fx is accumulating is
Constant
6 times,
the average change.
no, 6 times what?
The constant rate of change.
Is always 6 times, well, Josh, is that the constant rate of change?
Sorry.
Yeah, it's always 6 times
Your x value.
your x value. Whatever x value you're at. So it's 6 times the current x value. So the rate depends on what x value we're at. So, and whatever x value we're at, the rate of change of the accumulation of f is 6 times whatever x value we're at. Okay, so if x was 2.1, what can you say about the nature of the accumulation? Could you say, Tyler?
The rate is 12.6.
The rate is, he says the rate is 12.6. Yeah. Right, or in other words, r of, so we're going to use our x coordinate. Sorry, 6. Okay? And if the rate is 12.6, what does that mean for how x, for the quantities x and y? What does that mean, 12.6 mean, for the quantities x and y? So here we are. X is going along. The current value now is 2.1. The rate of change of the accumulation is 12.6. What does that mean for how the accumulation is changing?
In that interval.
So we're no longer at an interval. We're at an actual x value. Yeah, Connor.
So I guess what I was going to say is without the coordinates, the x value would be 2.1, then 12.6 would be added to whatever the previous y value was. I guess because that's accumulated y with 12.6, whereas
So what it sounded like to me is it said for a change of x of 1, y went up 12.6. Is that what you said?
well, it's the yeah.
Yeah, so that's pretty good. So for every change of x of 1, y is going to go up 12.6. So So this is going back to all that interpretation of what rate of change that we did before. So if 12.6 were a constant rate of change, what could we say about how x and y? What does that tell us about the quantities x and y? He said if x changed by 1, y would go up by 12.6.
Changes in y are proportion to the changes in x.
Okay. But so interpret this number 12.6. Autumn, any ideas?
I think the delta y would be 12.6 times relative to the size of it.
Yeah. Right? Changes in y are that many times greater than changes in x. This is rate of change. How about just y and x? What could we make a statement about the quantities y and x regarding this number? Anybody have an idea? Yeah, Nigel.
I mean, you could just expand delta y and delta x to y final and y initial, or is that not good enough? Like, y final minus y initial equals 12.6, x final minus x initial.
Okay, so, but I'm kind of looking for how are x and y changing together,
Oh, I see.
not an algebraic statement. Remember what we said? Dan, idea? Chelsea, idea? How is the f or the accumulation changing relative to x? Christina?
Is it just changing y over changing x?
Okay. That's true. Corey?
The y is, the changes in y are increasing 12.6 times the changes.
Just y.
Just y. Y is
Changing
12.6 times.
times as fast as x. Remember this?
Yeah.
So the accumulation is increasing 12.6 times as fast as x is increasing.
It's only 2.1, correct?
Only, exactly. Because what happens if we move to 2.5? What happened to the rate? The rate. So in a very small vicinity, good point. In a very small vicinity around 2.1, this is true. That y, the accumulation is growing 12.6 times as fast as x is increasing. But as soon as we get away from 2.1, what happens to the rate? It goes up, it changes, and so this is different now. You see? So you can still apply constant rate of change, but only over a very small interval. Okay? So as x goes from, say, 2.1 to 2.10003, how much does y change?
Much as y change.
Yeah. Or how much accumulation occurs?
0.00003 times.
Or how much accumulation occurs? Okay, work it out with the person next to you. So x is going to increase a very small amount from 2.1 to 2.10003. In that change of x, how much does y change, or how much accumulation occurs? Go, work it out. The what should not be there. Sorry.
It's okay. Just make sure it wasn't me.
Did you get it? Did you get it? So it's the third person next to you.
He's gonna give it back. So then over that, there's an
12.6 times 2.10. So
then you know that for the one to the other. Where
times
It's gonna be
delta x is 2.1
Actually, I'm not going to spend much more time doing this. So I'm gonna. Thanks. Okay, and then I want an approximate value using what you just found. Approximate the quantity, the accumulated quantity at 2.1003. Okay, so once you're confident about you got the change in y, how could you use that to approximate what the accumulated quantity would be at your final x value? Go, so you can do that.
We could either take
Okay, change in y. So in red here. So how can we approximate the change in y? Let's see, somebody new. Made any progress? Richard, did you make any progress on this? Yeah, what is the rate at 2.1? Yeah, so if the rate of change is 12.6, that means the accumulation is changing 12.6 times as fast as change in x. So you said it would be? I think it's 4 zeros, right? Okay, what do we get for that? 0.000.
378.
3 zeros?
Yeah.
How's that look? Yep. Right, because x changed this much, and right there in that vicinity, the accumulation is growing 12.6 times as fast as that. That's what rate of change means, right? It's going 12.6 times as fast as that. So how can we approximate f? We can use that to approximate f of 2.10003. Of course, we could take this and plug it into the function, okay? But we want to use the ideas here. How could we get our total accumulated quantity using this little change? Anyone come up with that? Tyler?
Did you just add that little change we just had
Uh-huh.
to whatever the value was at 2.1
And how could you represent that?
f of 2.1?
So he wants to take the starting value of the quantity and add the change. What do you think? Yeah, that's it. What do you get when you do that? So you're going to take 2.1 squared times 3 and add that. Tell me. 4 point? 12 point?
Accumulation at 2.100.
13.2 0378. Okay, this is a really important exercise because it's making sense of, so rather than just, oh, we got an accumulation function 3x squared, we got its rate function. So what is that rate? All these things I'm asking you, really seeing if you understand what that rate function means and does. Okay, really important. So it means that y is changing, or the accumulation is occurring 12.6 times as fast as x increases. So given any change in x, we can get that amount of accumulation in that for that little change of x, and we can use that change to approximate some total accumulated quantity. We just take the initial starting accumulated quantity and add the change, and we get the final accumulated quantity, which would estimate the accumulation at that final x value. Does it make sense? Anybody got a question? Yeah, Talia.
12.6 I thought was only the rate at 2.1.
Right.
So then at the top when you do the change of y, it's about 12.6 times that.
Right.
I guess I'm just confused from there, like that.
Okay, so how much change in x do we have from 2.1 to 2.10003? The big change or a small change?
Small.
So we're basically assuming that in this very small vicinity of 2.1, we're using constant rate of change.
Okay.
We're assuming a constant rate of change over that small vicinity. Now, if I'm going from 2.1 to 2.6, this is not going to work because that's too big of a change. The rate changes way too much over that interval of x. But we can do this, and also why I'm making wavy equal signs, right? So I'm just saying approximately. So it's because we're only looking just around, very close to 2.1. We can assume constant rate and make these approximations. Does that answer it? Good question. Other questions? Yeah. Oh, sorry. Autumn.
Why wouldn't you plug in 2.0003 and use the rate for that instead of 2.1? I mean, it's like barely different.
You mean in this calculation right here?
In the top calculation.
So we could exactly find what the accumulation is just by plugging this into the accumulation function. But so if for some reason that was inconvenient, it was a lot more convenient to use this, right? Because that's actually a much easier calculation than this one, putting that into the function than this one. So that might be one motivation why we might do this. But it was a question to test your understanding. And you're right, the true answer to this is just by plugging in that final value of x into the function. But that was just an exercise to kind of test your understanding of the quantities and what's going on. Okay, still other questions? Okay, they're both exact forms. So it's not that this one's exact and this one isn't, right? The integral is an exact form. What's the difference? And we talked about this Friday. There are two different forms. This one shows the process. What kind of process does it show? What's that? Yeah.
The difference is that the accumulation can start at any point, but the rate of change won't indicate that because the rate of change only. I'm sorry,
Okay, so
they're the same thing.
okay. But how is this representation different than this one? What is this representation showing that this one isn't? Yeah, Sharon.
The interval function shows the bit accumulation.
Right, it shows the process of summing up the bits, right? It's the process of summing up, right? German S means sum, and these are our bits, right? Rate times little change in x. So it shows the process of summing up the bits. We call that open form. Okay? This doesn't show the process, but it can spit out accumulations for any value x, amount of accumulation for any x that we put in. That's what we call closed form. So again, open form shows the process. Closed form is kind of like the rapid fire version of getting amounts of accumulation. But they both produce the same value for a given value of x. Okay? Similarly here. Which one is exact and which one is approximate? Which one is exact and which is approximate? Both exact, right? This is exact. When we were saying take that limit as h approaches 0, we get the exact function, but we know that we showed algebraically that it's the same as 6x. Okay? So what's the difference? What is this one showing that this one doesn't? What process? Yeah, what process? What process does it show? Autumn.
Taking the limit, like showing us x approaches 0.
Say, but where did this process start? That was actually that kind of the last step of the process. So what, Corey?
That's the change in y. So like the little bits of change as you and your y.
Not quite. What does this? What process is this showing? Autumn again. Yeah.
Shows separating the intervals with delta x.
Separating the intervals with delta x. Okay, it's part of it. It shows building what? What does this show building, Connor?
Finding the average rate of change across small intervals.
Yeah, the average rate of change function, right? Our piecewise, this shows that process of building the piecewise linear function that has all the average rates of change. And as the limit goes to 0, we get that exact function. So, left one is open or closed? Open shows the process of building the average rate function. This one just spits out rates for any value x, closed. But they give they're the same function, but just a different representation. Process version, rapid fire results version. You see? Okay, so I think for just one more, did you have x to the 4th in your homework? Okay, and what did you find for the rate there? If you do the math, you should have gotten 4x cubed. So how could I write x to the 4th as an accumulation function like before? 4t cubed dt. Okay, so I hope today's class is kind of starting to tie this next chapter together, things that we're doing. Homework is posted. If you want to come get your quiz on Friday.
Well, what if he gives me, well, we got 100 on it.